Good morning, good early afternoon, whatever time it is for you, to everyone. My name is Matthias Magdowski. I'm a Chief Reverberation Officer at the Otto-von-Guericke-Universität of Magdeburg in Germany. No, I'm kidding. I'm a scientific co-worker there. And yeah, so this is first part of two talks about reverberation chamber measurement. And I've entitled this talk Robust, Precise, Fast, Choose 2 for your radiated EMC measurements. So it's a bit challenging to give a motivation about EMC at some EMC conference, but there is this problem of electromagnetic compatibility or incompatibility. Devices over radiated fields, for example, might disturb each other. Your Wi-Fi router at home might disturb your TV set or Bluetooth headset, or the microwave oven might disturb the Wi-Fi router, something like this. And so the question that we all deal with in electromagnetic compatibility is, will there be a disturbance or not? And will there be some interference, and how can we measure this? So to test this, we go to labs and we do measurements, and these measurements are done according to standards. And then the question is, do you as a test engineer more or less just follow the standard, what is written there? Or do you also try to understand the physics behind this test? And I would strongly encourage you to also question yourself a little bit here and there, and to also try to understand the physics and to not be the test engineer that just applies the standard. Because these standards are all a little bit like a recipe, and my example always, you also need to understand this recipe a little bit to apply it. Because if you, I don't know, if you give a birthday party, and if you want to bake a cake and you expect more guests than usual and you want to double the cake, okay, you need double the eggs, double the flour and so on, double the sugar, but you don't need to set the oven to 400 degrees Celsius. So you need to understand what the recipe really means. This is the same for standards. And a very fundamental question related to electromagnetic compatibility and radiated emission measurements is, what is a good measurement for this? Is it field strength in a certain distance, as we do and as we have done for years and for decades? Or is it, for example, power flux density, as it's done in communication and IT, cell phones and stuff? Or is it total radiated power, as what is, for example, measured in reverb chambers? And another question is, what is a good replica of the real life? Is it really the perfect anechoic environment, totally free of reflections, or maybe there's just this one reflection from the ground? Or is it an environment with high reflections? If you, for example, look at the space we are here, so there's lots of metal at the ceiling. If you are in an industrial environment, you would expect many reflections if you are in a car, in a ship, fuselage. Or is it really highly, highly reflective as in a reverb chamber? So, after this short motivation, I would like to give a brief introduction into semi-anechoic chambers, then into reverberation chambers, then try to look at how can we convert results from one environment into the other environment. And one important property in this section will be directivity of equipment under test. Then show some exemplary measurements that a colleague of me has done in Magdeburg a couple of years ago, and of course at the end there will be a quick summary. So the idea of semi-anechoic chambers is, if we want to do, in general, radiated electromagnetic compatibility tests, we need to shield ourselves from the environment. Because if we want to measure emission of some equipment under test, we only want to measure the emission of this equipment and not all the radio, Wi-Fi, TV, whatnot, signals from the surroundings. So we need to shield ourselves from the environment. This is done with metal. And metal works for electromagnetic waves like a mirror. That is nice. So everything that comes, let's say, from the outside is mirrored back, but everything that we generate on the inside would be also mirrored back from the walls. And so now imagine you're in a room full of mirrors, you switch on a flashlight. What will happen? You see light from all the directions, from everywhere. You don't know anymore where's the light coming from, where will the light go, and so on. And the same thing will happen in a shielded enclosure. And so what could we do with the mirrors that they don't mirror anymore? Like in the Rolling Stones song, Painted Black. take some black paint and paint the mirror black, and then it won't reflect anymore. And the same thing we would like to do in our semi-anechoic chamber. So we take this big styrofoam, for example, absorbers, and they will like absorb the electromagnetic waves so that they cannot be reflected from the metallic walls. And then there's usually a turntable. You can place the equipment under test on a turntable and measure the emission in terms of field strength in a certain distance with some antenna, and rotate this, for example, and get a radiation pattern, a radiation diagram of your equipment under test. And this is how it looks like in practice. So this is our big 10-meter measurement distance semi-anechoic chamber that we operate in Magdeburg. As far as I know, we are the only university in Germany that operates such a big chamber. This is quite an old photograph. The newer one, or we have an updated version with smaller absorbers at the end, because we have a big, instead another big door where we can put or place big cars inside the chamber, like up to the size of an ambulance car, let's say. And so what we would like to measure there is really the radiated field strength in the far field. That's why we need this big measurement distance, 10 meters, to be able to measure starting from 30 megahertz. And we want to, in general, measure the emission over all directions. That's why we do this rotation. What we really measure in practice is, okay, the radiated field strength in a certain distance, but we cannot measure all directions because it would take horribly long time, especially if the radiation pattern is very complicated. So we do, for example, just one spherical cut. And we do not really measure, at least for large floor standing equipment, it is not rotated, only the emission to the side. We don't measure what is radiated to the top. We don't measure what is radiated to the bottom and might be reflected. And okay, maybe not here, but in general, there might be also other equipment above you that might be disturbed by radiation. Okay, so after having a look at anechoic chambers, let's have a brief look on reverb chambers. So in general, this is also some shielded enclosure. But here we would like to work without the absorbers. So for example, if we let one antenna radiate, or if our equipment under test radiates, it will, let's say, create, as a very simple model, plane waves, and the plane waves will travel through space, and they will be reflected. And they will be reflected back and forth and back and forth. So you have lots of reflections of, or you get a superposition of traveling waves in opposite directions. So what you get is standing waves. We get a standing wave pattern. We get points in space where the field strength is really high. These are the antinodes, and we get points in space where the field strength is very small. These are the nodes of the standing wave pattern. And so, for example, for an immunity test, now you would need to take your equipment under test, carry it around, and find the position where you have a high field strength. Of course, you would not like to do this. So the saying is a little bit, it's a little bit like in the saying, if the prophet cannot go to the mountain needs to go to the prophet. We would like to keep the equipment under test in place, and we would like to move the field around. And moving the field around works with a large metallic object with large metal surfaces that change the reflection of the waves. And by changing the reflection of the waves, we also change the standing wave pattern, and we move the this field around. And yeah, on average, we get some homogeneous and isotropic field on a statistical basis. So the field strength does not depend on position, does not depend on direction. And these standing waves in electromagnetics are called modes. And with this large metallic object, we kind of steer the modes. That's why we call this a mode steerer, and the whole thing a mode steerer chamber. But because there's also lots of echo and reverberation of the field in there, you can also call it a reverberation chamber. And since maybe, let's say, 10 years, this is the more common term to call it a reverb chamber. This is how a practical chamber looks like. This is the chamber that we operate in Magdeburg. This picture with the motorcycle is very popular. If you check the If you check the English Wikipedia website for electromagnetic reverberation chamber, you will also find a picture there. The motorcycle actually never was tested. It was just placed into the picture to make the picture look nice. It was a motorcycle of a former student. But this somehow worked out. And at the end, it's just a large microwave oven. And yeah, a good question that someone asked me a couple of years ago, also I think at some EMV conference, is, hey, Matthias, you operate these reverberation chambers, right? If you hit one of the resonances of the chamber, don't you get some incredibly high field strengths then? And I said, yes, we do. And if the chamber is properly operated, we not only hit one of these resonant frequencies, we always hit a couple of these resonant frequencies at the same time, because otherwise our field statistics would not properly work. So yes, it's always in resonance. We always hit many of these resonances. And to change the electromagnetic boundary conditions, you can have a rotating stirrer. You can try to move a wall. You can change position of antennas, switch between antennas. And for immunity tests, you can also, of course, just change the frequency with your signal generator, which is called frequency steering. Another idea, this has been made very popular by my colleague Frank Levering from University of Twente in the Netherlands and Thales, is to use these vibrating intrinsic reverberation chambers or works. Just use a tent out of metallized textile, shake the walls, move the walls, and then you also get nice changing field pattern inside and can do statistics with this. This is a picture of such an oscillating wall stirrer. From my point of view, this is not super practical, but it's a nice academic approach, let's say. And yeah, so the properties, as already mentioned, is we want to have a homogeneous field. Field should not depend on position, which allows us for free placement. We want to get some isotropic field, so the direction of the EUT and of cables and stuff like this should not really matter. And this is, of course, only valid if we are in a certain distance from the walls. Close to the walls, the field will not be homogeneous and not be isotropic, because the boundary condition at some metallic wall is always that the tangential electric field and the normal magnetic field must be zero. So you need to keep a certain distance from the walls. And at the end, a reverb chamber is just a larger microwave oven. In a microwave oven at home, you cook chicken. In our reverberation chamber, we cook electronic chicken. We test devices for immunity or for emission. Okay, so what we would like to measure there is total radiated power for all frequencies. And what we actually measure is total radiated power for all frequencies. Of course, there is some intrinsic field uncertainty. So the result is a little bit falsified by this due to remaining inhomogeneity of the field and a limited sample size, right? The result depends. It's a little bit like throwing a dice. If you throw a dice, the average value, the expectancy value would be 3.5 if you have a normal dice. But if you just throw the dice 10 times and calculate the average, you will not get close to 3.5. If you throw it 100 times, you will get closer. If you throw it 1,000 times, you will get closer. So we need many samples to do good tests. And one problem is, okay, we can measure this total radiated power, which is very nice and robust, but there's no limit for this. The limits are all given, or most of the limits are given in field strengths in a certain distance. This is certainly a problem. So, and this brings us to the next section, and the next section is, okay, how can we convert the results between total radiated power and field strengths in a certain distance? And for this, we somehow need to define what is called the electrical size of our equipment under test. So this should be our equipment under test. And let's draw a circle, or in 3 dimensions, a sphere around this. And then K is the wave number and A is the radius of the sphere. And the product of the two is the electrical size of the object. It's a dimensionless quantity. And okay, if there are cables attached to the EUT, do they belong to this? To which length cables has to be considered? But okay, let's say we have some equipment, we put a sphere around this, and K times A is the electrical size. So now if this electrical size is smaller, much smaller than 1, we have no problem because everything radiates like a dipole. And the radiation pattern of a dipole is a donut that you might get at the coffee counter here. And so finding the maximum radiation of this donut-shaped dipole radiation pattern is quite simple. If you rotate it in, let's say, 90-degree steps, no problem, you will find the maximum emission. Problem is, if we go to higher frequencies or to larger objects, so if this product K times A electrical size gets larger, you can get more complicated radiation patterns. And there's a nice video that former colleague Magnus Höjer from the FOI, the Swedish Defense Research Agency, created, I think, 15 years ago. But it's still very up to date. So they took a large. I will start the video first. So they took a large equipment under test, some cabinet-sized case, and let it radiate and measure the emission, the radiation pattern in one spherical cut for frequencies starting from 0.5 gigahertz to 20 gigahertz. And so you can see how this radiation pattern changes over frequency and also how the maximum changes. And sometimes it points in this direction and sometimes it points in this direction. And remember, what you would like to do in a semi-anechoic chamber is you would like to find this maximum radiated field strength in a certain distance, but you don't know the direction. No one knows the radiation pattern of its equipment under test. So it's really, really challenging to find this maximum emission and to select what step size do you choose. Do you go for 90-degree steps, 30-degree steps, 10-degree steps of your turntable to always be able to capture this peak that also moves around here. And another problem is if I move forward here a little bit in the video and go to higher frequencies, so now we are at almost 12 gigahertz, is that you see that this radiation pattern, that the radiation lobes get narrower and narrower, almost pencil-like. The radiation pattern looks a little bit like a hedgehog. Because it's some unintentional radiator, these lobes approximately all have the same size, but still it's kind of difficult to find the maximum. And here you can see you would need to go for very, very, very small degree steps with your turntable in the semi-anechoic chamber. So that's definitely a problem. So the higher the frequency, the higher the problem. And the longer you would need to wait, or the more smaller steps you would need to measure to find the maximum. So this is definitely not practical. Still, we would somehow need to or like to convert the results, and what we need for this is a quantity called directivity, and this is the ratio between, let's say, the maximum radiated power in the main beam direction and the average radiated power. And for a short dipole, this is known. This is 3/2 or 1.76 dB. And for electrically large objects, it's growing with frequency. And if we have this directivity, then it's not such a big problem to convert total radiated power into maximum field strength in a fully anechoic room or in a fully anechoic environment. And we can more or less apply the very same formula also in a semi-anechoic environment. But here we need to include an additional geometry factor that takes into account for the reflection at the ground plane and the superposition of the direct and indirect path in this case. So this is all known. Still, we need to have this directivity there. And there are different models to estimate this directivity, and the one that I have used was developed by Hans-Georg Krauthäuser, also a former colleague that now works at the Technical University of Dresden, and it has been published in the IEEE Transactions almost 15 years ago. And so with this, you can model it. So this model here is based on, we take a large sphere, or we take a sphere of the size of the object, put point sources on the sphere, and then calculate the directivity calculate the radiation. And with this, you can then do this conversion. And so what I've shown here is semi-anechoic chamber to reverberation chamber with respect to frequency for a certain object size and for a certain measurement distance. And so the result here is directly maximum field strength or maximum field strength squared to total radiated power. And you can see that for low frequencies, it's staying constant, and then there's some break, and then it increases with higher frequency. And so this is a similar result for a fully anechoic room. So here these dips, let's say, in the curve, they are due to the reflection on the ground plane, the influence of the ground plane. Here we have no ground plane, so there are no dips. And so these different curves are the average value, the median value, and the statistical spread. So 90% of the values would be in this range. And if you like, I will share my slides later on LinkedIn. And I will also share these links. If you click on these links, you will go to some Octave online website and you can repeat the simulations there. So it's a statistical simulation. You can also change the values if you like, go for different frequencies, go for different sizes of the object, go for different measurement distances, and so on. And so because there's no influence of the ground plane for the fully anechoic room, here you could also directly scale it to this electrical size, and then you can see, okay, if the electrical size is smaller than 1, it stays constant. If we go for higher frequencies, then directivity in general increases. So the fundamental question now is, which type of measurement environment would you like to have for your test? Would you like to go to the semi-anechoic chamber where the environment is deterministic, everything is perfectly fine. You know, okay, I get a field from this direction, I have this antenna distance, and so on and so on. But your equipment under test is random. You don't know the radiation pattern of your equipment under test. You don't know which step size do I need to choose to really capture and get maximum radiated emission. It's absolutely unknown. And the higher the frequency, as we have seen, the higher the problem there. Or would you like to go to the reverb chamber? So here the environment is kind of random because you have this remaining field inhomogeneity, you have remaining anisotropy, but your EOT is deterministic. It does not matter what is the radiation pattern of the equipment under test because you will be always able to capture the emission. It will not matter in which direction it will radiate. It will be always reflected by the walls. It will always end up at your receiving antenna. So from my point of view, this is much better. And the randomness here, you know, and you can control because this is determined, for example, by the number of stereo positions that you measure in the reverberation chamber. And let's say the general quality of your chamber and the steering process and so on. So to go for higher frequencies, this is, from my point of view, the much better choice. To demonstrate this a little bit, I can show you some measurement results that another Mathias, which is a very common name in Germany, to be honest, but he has 2 T in his name. My parents were poor, we could just afford 1 T. So he has also done measurements in Magdeburg, and as you can see, he used a fairly large object with some, let's say, loop antenna, something like this on the top, and the comp generator inside, and tested it in the reverb chamber and also tested it in the semi-anechoic chamber. And here are the emission measurements converted or displayed in maximum field strength in a certain distance. And the blue curve is the result from the anechoic or semi-anechoic chamber. And the green curve is the result from the reverb chamber. You can see that there's much more variability or spread in this reverb curve because this is, let's say, the intrinsic statistical uncertainty of the reverb chamber. And so the conversion here has been done with a directivity with, of course, a wrong directivity, but with an assumed directivity of 1. So the difference between the 2 curves is more or less due to the directivity of the object. And yeah, we can see that I think this semi-anechoic measurement has just been done with 10 degree steps or so. So we can see, okay, there is some difference between the two curves. It's not really growing with frequency because very probably at high frequencies we are not really capturing the maximum anymore. And this can also be seen here. So these are measurements with, or this is the measurement analyzed in terms of different step sizes. So the green curve is just with 90 degree steps, very coarse stepping of the radiation pattern. And the blue curve is the one with 10 degree steps. And you can see that there can be very large and notable differences between the two curves. And if we would go down to 5 degree steps, 2 degree steps, the real maximum might be even higher in this case. Okay, so let's come to a summary. Question is, so still we would like to measure radiated emissions of general devices. We want to have robust tests, and in a semi-anechoic chamber, what holds us back a little bit is the unknown radiation pattern of the equipment under test. We don't know this, that's why we don't know for which steps we should go and so on. And there would be a solution. Yeah, we could go to reverberation chambers, measure total radiated power there, independent of position and orientation and so on, very robust for all frequencies. But unfortunately, there's no limit for this. We don't have total radiated power limits. We only have limits in terms of field strengths. So all good things are never together. In general, we would like to have robust, fast, and precise tests. So the reverb chamber is robust and fast, but it's not precise in terms of repeatability, right? You always have these field statistics. The semi-anechoic chamber with full sampling, this would give us a robust and very precise result, but it would take very, 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 very long time. So it's not fast. And the semi-anechoic chamber with undersampling is precise in terms of repeatability and fast, but it's not robust. The result depends on where you place the equipment under test, how are cables oriented, will the cables go to the side and then to the ground, will the cables go directly to ground, what will be the termination of the cables, and so on and so on. So yeah, the perfect test unfortunately does not exist. This finishes my talk. Thanks for your attention, and I would be happy to also answer some questions.
Can you combine the two techniques and try to find some balance where you get the center best of all worlds?
Yes and no. So I would say the existence of reverberation chambers is not really the end of anechoic chambers, because reverb chambers always have a problem going to low frequencies. If you want to do emission measurements or immunity tests starting from 30 megahertz, it's very, very challenging to build a reverberation chamber for this frequency because it would be very huge. Let me take this. The reverberation chamber has always advantages for the high frequency range. But the problem that I see is that people are so used to semi-anechoic chambers because this is the main test environment for radiated immunity and emission, that they would also like to continue to use them for frequencies above 1 gigahertz, above 6 gigahertz. Now people are discussing to do EMC measurements, extend the frequency range to 40 gigahertz. And at 40 gigahertz, from my point of view, it's total nonsense. It's really stupid to do emission measurements in semi-anechoic chambers. It simply does not make sense.
A question with the stereo, which kind of mode we can achieve, in fact, in terms of TE or TEM, I don't know, or TM? Or
in general, I would say the reverb community does not care about if it's TE or TM mode, because we always, if you have, usually it's not a perfectly cuboid resonator, and we have many objects in there, the antennas, the stirrer, other tripods for stuff. So we never anyhow get these perfect TE or TM modes, and at the end we would just want to have a sum and superposition of many modes that are as complex as possible. So we don't care about this.
Excellent. Thank you, Mathias. Okay, I'm going to talk about the immunity side of reverberation chamber testing. And specifically, I'm going to look at some actual test results following one of the new reverberation chamber standards on how that compares to some of the other existing reverberation chamber standards. So I'll talk a little bit about the IEC documents, 61004-21, a DO16 standard, and the procedures that are used in those two documents, and see how that compares to the new techniques that are suggested in the ISO 11451-5 standard that we will probably see in the 452-11 standard as well, sometime in the very near future. This is all related to immunity testing. Mathias talked a lot about emissions and some of the pros and cons of reverb testing versus an anechoic chamber test for emission measurements. What I'll talk about is immunity measurements and the automotive industry, and why the automotive industry is tending towards the use of reverberation chambers for some of these immunity tests. So here we have a typical setup, reverberation chamber environment with a vehicle under test. And in the existing IEC standard, the way the chamber is characterized and used is fairly different to what's suggested in the IEC document. So on the left here, I show the formula that's used for calculating the input power required for your target electric field based on chamber characterization and normalized field measurement. And similarly, the procedure that's used in the DO160 document, where again you characterize the field, you measure the uniformity of the field by sampling at a number of points around your test volume, calculate the variation of the field, and then use some of that data to calculate or predict the input power needed for your test field strength. In the the ISO document, the procedure is a little different. And the method I'm going to focus on is what's called the closed loop method. And this involves the use of multiple probes so that you can sample multiple probes simultaneously, do the calculation of the statistics of the field on the fly, and normalize and level the field all in one sequence during the course of the measurement. And of course, the big advantage with doing that is you save a lot of time. The big disadvantage is that you've now multiplied the number of field probes that you need. So you drive a little bit of the cost of the test setup up by doing that. But you save a lot in measurement time and improve a lot of the statistical response by having the ability to sample the field very, very quickly at those 8 positions. So the data I'll show is based on a couple of measurements. The first one is using some of this equipment, typical RF immunity test setup, where you have your signal source, your amplifiers, multiple field probes in this case, and then you'll have your device under test, in this case a vehicle, in the middle of the reverberation chamber. Other pieces of equipment, obviously you have your transmit antennas, maybe a receive antenna is optional, but most of this is equipment that you'd normally have when doing an immunity sort of measurement in a reverberation chamber. The big changes here is the use of the 8 probes simultaneously, all sampling on the fly during the course of the measurement. And then RF tuners, various speeds. The standard now supports what's called high-speed stirring so that you can really stir those modes very, very quickly and take advantage of probes if they're very high-speed probes. So the first question is, well, how accurate are these probes when we are sampling very, very quickly? And what my colleague did was just a quick run showing the sort of variation in measured field as a function of samples. And you can see it's a fairly stable response. It's varying by a few tenths of a volt per meter at about 48 volts per meter during the course of that test sequence. So we're fairly confident that the probe is fairly stable and fairly accurate in the measurement. The next thing he did was arrange the probes around the test volume. So we have the upper range or upper row of probes. And at the bottom here, we have another 4 probes at the bottom of the probe stands. Ignore this little turntable. That's there for a slightly different reason in this chamber environment. But he's got the 8 probes set up, transmit antenna on the far wall, and the tuner, obviously, for stirring those modes. And what he's going to do is just rotate the tuner, stir the modes, and sample those 8 probes on the fly. And while he's doing that, he's measuring the maximum, the minimum, and the average, and calculating those values during the course of the measurement on the fly. Okay, so the first environment is a 200 megahertz chamber. You can see the dimensions of the chamber at the bottom here. Fairly typical size that's used for component testing in the automotive industry. Frequency range is about 200 megahertz to 3.5 gigahertz, covering the CW and radar band of measurements. There again is the test setup. And what I'm doing here is comparing the IEC procedure with the ISO procedure. So for the IEC method, the usual method is to move a single probe to 8 individual positions and repeat that frequency range 8 times and then do the math, calculate your normalized field, and then do the test as a separate measurement. That obviously takes a lot of time. And one of the methods in the IEC standard is a step method. And you can see the number of tuner steps, 50 individual positions below 600 megahertz. And in this example, about 20 steps above 600 megahertz to a gig. So a fairly time-consuming process that takes several days moving that single probe around for those measurements. So let's look at some of the first set of results. So this is the normalized field. You can see measured in volts per meter per watt on the left axis here. The red curve shows the maximum of the maximums of all 8 probe axes, you know, the 3 axes of each probe in all 8 probes, or all 8 probe positions. This shows the max of the maxes. The average of the maxes is the faint blue line, and then at the bottom in dark blue, we have the minimum of all the maxes. So we can see that in comparing the maximum measurements of all 8 probes, we can see how that maximum varies over those 8 probe positions using this IEC procedure. So fairly wide variation in the measured maximums with those 8 positions. If we compare that with the ISO procedure where we have the 8 probes measuring simultaneously, and in this case we are rotating the stirrer continuously, so we're stirring with a rotation speed of about, I don't know what the speed is, but the rate is about 7.2 seconds per rotation. And the sensors or the probes are sampling at about 70 samples per second in this case. So over that complete sequence, he's recording about 577 samples of the 8 probes. So as Mathias touched on, the standard deviation that you calculate is a function of the number of samples that you take. So compared to the IEC procedure where we are taking 50 tuner positions or 50 steps, hence 50 samples, here we are taking several hundred samples. So we have a much higher sampling rate because we have the ability to do that with the faster probes. And we've multiplied the number of probes, so we would expect to have fairly good statistics with this measurement. So if we compare the variance that we see in the field, here again we're measuring the max of the maxes, the mean of the maxes, and the min of the maxes, the red, blue, and black curves here. And on the right, we are looking at the variation. Nope, sorry, this is just the mean of the maxes. So this is the blue curve taken out. So we can see the variation in the mean is not very wide. And when compared to the spread that we saw with the IEC procedure, the red curve here is showing what we measured earlier with the IEC procedure, where we were almost 30 volts when we look at the max of the maxes compared to the min of the maxes. When we compare the similar variation used in the ISO procedure, the black curve is at speed 6 for the measurement, and the blue curve is at speed 8. So we are taking more samples at the highest speed, therefore we have less variation between the max and the min measured using those 8 probes simultaneously. The black curve is slightly slower stirring, but again, comparing the max to min of those 8 probes. And we see we have a fairly tight variation in max to min using the IEC method, sorry, the ISO method, compared to the IEC method at low frequencies. And obviously that spread is bigger at low frequencies because you have fewer modes, and it's much harder to store those fewer modes at the low frequency than it is at high frequencies. So as again, what you'd expect to see is these sort of coming together as you go up in frequency, because stirring efficiency improves even using the IEC method. So a very good indication that by virtue of the fact that you have very more samples and you're making measurements with those 8 probes simultaneously, you've sort of improved the statistical data that you're able to capture with that fast probe. The other advantage is measurement time. So with the stirring and the 8 probe method, we've now reduced our measurement from days to hours. So we no longer have to move that one probe to 8 different positions. We're taking all 8 measurements simultaneously, and we can do that in a matter of a couple of hours, obviously depending on frequency, step size, and stirring speed. So it stands to reason that if your probes can read fast enough, and you can stir those modes fast enough, then you can reduce your chamber characterization time significantly by doing that. So here's another set of results. This time it's in a larger chamber. This is an 80 megahertz chamber now, large enough for sort of full vehicle testing. The frequency range is a little wider in this one. You can see the full chamber there. Again, we've got the 8 probes, the upper and lower 4 probe positions. And the odd thing about the automotive standard is that the lower probe position is not necessarily coincident with the lowest position of your DUT, your device under test. Because most vehicles will be sitting on the floor of the chamber, maybe on a chassis dynamometer. So you'd be really interested in understanding what your field variation is going to be close to the floor of the chamber when doing that type of measurement. So what he did here was looked again at the characterization of the chamber across that frequency range, looking at the variation of the field as a function of frequency, and looking at what impact that has on the variation in field strength during the course of an immunity measurement. So here now we're looking at field strength, calculated field strength versus the measured field strength during the course of an immunity measurement. The blue curve is the scaled forward power calculated from this relationship, and the red curve is the actual measured, or the average of the measured forward power at the 8 field probe positions. And here you can see that variation in the average is fairly close to the calculated value based on those 8 probe measurements. And if you factor that into an actual immunity measurement, you can see in this example where your target field strength is 100 volts per meter, your variation in field is fairly tight. And in a reverb environment, this is a pretty good result, and really as good as it is purely based on the fact that you have sort of hundreds of samples that you're using during the course of that statistical analysis. Again, the advantage here is that you're able to take a high number of samples. We're measuring about over 500 samples per second with those 8 field probes, doing the statistical analysis of the average field, and then leveling up to that target field level based on those 8 field probe readings. And if we look at the max, the max of the max, the mean of the max, and the min of the max, again, depending on which one you want to level on, you can see that you have fairly good stability in the variation of those values across the frequency range. So a very, very good method to improve the stability of your measurement environment. And again, compared to the IEC standard, fairly low variation in the max to min of the maxes when using that 8 probe ISO setup compared to the traditional IEC type environment and IEC procedure that was used previously. And of course, the big advantage here again is that you're saving in measurement time because you're doing that analysis and measurement on the fly. Okay, so let's look at the standard deviation of the field that you would expect given the increased sampling and the use of the 8 probes in sequence. So this calculation now is looking at the standard deviation of the field, and it's again based on the traditional method and comparing it to the ISO method. We can see that here we have a fairly good field uniformity at the low frequencies. This limit is taken from the ISO standard 451-5. You're allowed to have a field variation as much as 6 dBs at that low frequency. And here you can see that we have fairly good control on the field environment, again, mainly due to the high number of samples that are taken. Oh, one thing I wanted to mention here is the height of that lowest field probe position, 90 centimeters above the floor. It's greater than that quarter lambda that Mathias mentioned to make sure that you're within an environment where you can have good field variation. So we're not too surprised to see that we have good field uniformity at those low frequencies. One of the things we wanted to look at was what impact reducing that minimum probe height would have on the uniformity of the field. And as you can see, as we reduce it to 60 centimeters, things start degrading slightly. We go down to 30 centimeters, we get a little more variation as we go down towards the floor of the chamber. But for some of the measurements, we found that you can get quite close to the floor, less than that quarter lambda, and still have fairly reasonable field uniformity. And the reason why this is important is because in some cases, you might have some electronics, tire pressure monitors, for example, that are fairly low in the field environment that you want to make sure still gets exposed to some of that statistics of the reverb chamber. So understanding what your field uniformity is close to the floor may be a useful advantage in being able to do those measurements. So we can see here that even close to the floor, we still have fairly reasonable uniformity, although we're not quite meeting the limits of the standard across the entire frequency range. And of course, one of the big advantages here, again, is the saving in time, because now you're not doing a separate field uniformity analysis where you're running the characterization of the empty volume and then doing a separate measurement of the DUT loading and then doing a test based on those prior measurements. You're doing all of that on the fly in one sequence of measurements. So it's a very big time saving in being able to do that. And that's one of the big benefits and advantages of the procedure that's suggested in this ISO standard. And as I said, the intention is to try and bring some of these procedures across to the component version of that document, which is the 452-11 standard. So that will also include some of these, multi-probe method and fast stirring and VIRC tests procedures that were mentioned earlier. So with that, are there any questions for me?
You use 8 probes. What is the field in the middle of this cube? Let's say this cube. Why? What can you expect? Because it is, is just.
So we would expect the statistical variation everywhere to be the same. We pick the 8 corners of the cube, but it's not necessary to say that 8 corners have this behavior and the rest doesn't. So all of the chamber environment away from that lambda over 4 from the surfaces should see the same statistical variation in the field.
It is based on what? We can say this law or this rule.
There's maybe I should go a little bit away from the speakers. There's a statistical rule for this, which is not so commonly known. It's called ergodicity. And ergodicity means that you can interchange different statistical ensembles. So, for example, if you take a field probe, you leave the stirrer in place as it is. You take the field probe and move the field probe around. You get certain statistics, and you get some average value, some spread, some standard deviation, something like this. And so now you take the field probe, leave it at one position, and measure different positions of the stirrer and do statistics. And due to ergodicity, you would expect that you get the same statistics. And so usually for some humidity test, for example, you would like to measure the field at the equipment under test. So you could take the equipment under test out of the chamber, put the field probe there, measure the field at exactly this position. But if you introduce the equipment under test, because it's so strongly coupled to the reverb chamber, you would change the field anyhow a lot. So you can never measure the field exactly at the position of the equipment under test. You can only measure it at other positions, and then due to field homogeneity and isotropy and so on, say, okay, at the equipment under test, within this spread, I expect to have the very same field.
Yes, and there are 2 things that I would add to that. The first one is the fact that, as you can see in this illustration here, where we had fewer samples with the IEC method, you can see that you're getting a bigger spread in that measured field. And all that means is that you're undersampling, because we're in the same chamber. Nothing's changed electrically or electromagnetically in that environment. All we're doing is sampling in more positions by having more probes and more tuner positions, so we're taking more samples. So nothing's changed electromagnetically in the environment. The only thing that's changed is the number of samples. So, and it doesn't matter where the probe is, we would see the same statistical variation in field everywhere within that test volume in the chamber. Exactly.
Yes. Node sample from the probe measuring the field?
Yes.
But
and we're changing the boundary conditions by rotating that stirrer.
Okay, thank you.
Okay. Any other questions? Question, Vignesh?
Yeah, Garth, would you mind going back to your slides 25, 26, and 27? So that's 24. So here you're talking about the 90 centimeters, and the next one is 60, and the next one is 30 centimeters. Would you comment on the peaks that you're getting around that 900 megahertz?
Yes. So this is a resonance that we have in the chamber. It's an anomaly. It's a bias that we have in the chamber that may be related to the position of the field probe relative to some reflecting structure. So we have that standing wave that's causing this anomaly at this frequency in the chamber that they didn't recognize when they did the measurements.
And to add one more comment, you kept saying several times that now we have 8 probes and we're making more. I mean, we're making better measurements with more samples, so on and so forth. But you also made a comment that, physically nothing else is changing inside the chamber, right? I mean, you've got a certain amount of energy that's going in, and for that energy, you have a certain amount of field that exists. So, and just because we're taking more measurements, does that mean that, you're going to get a better chamber or not a better chamber?
Well, you're getting, well, theoretically, yes, and theoretically, no. Because the chamber environment's not changing. All you're doing is sampling, so they have better statistics. But the environment's not changing. As long as you have the same rotation of the stirrer, you have the same variation of the field or the modes within that cavity, that stays the same. All we're doing is changing the number of times we sample that field. So if we take one sample, we get one number. If we take 100 samples, we get a much greater chance of measuring what the peak is in that environment. But the environment itself hasn't changed.
Of course, we want to collect many samples, as said before, because more samples mean more or mean less statistical uncertainty, but the samples need to be statistically uncorrelated, or they need to be independent of each other. And so if you have just one stirrer, if you rotate it 360 degrees, after this you will get the very same, or more or less the very same samples again.
Thank you very much. Thank you. Thanks, Matthias.